Have you ever looked up at a skyscraper and just felt this sense of awe and maybe a little bit of disbelief? I mean, how do these massive structures, seemingly just defying gravity, actually stay up? Well, in this explainer, we're going to pull back the curtain and reveal the hidden engineering principles that keep our entire world standing. Right? You see a tower of glass and steel just disappearing into the clouds, and it's so easy to think there must be some kind of magic involved. But here's the thing. It's not magic. It's something way more impressive. It's brilliant engineering. So let's dive in and find out how it all works. Okay, to really understand any of this, we have to start with the most fundamental principle in all of architecture. This quote from the engineer Heino Engel is basically our key to everything. It completely flips the old way of thinking on its head. See, we tend to think a building's support system, its bones, is just something to be hidden away. But that's not it at all. The structure is the very thing that gives a building its shape, its character, and you know what? Even its beauty. So, how do engineers actually bring this big idea to life? Well, they have this incredibly powerful toolkit, a set of 4 structural families that can be used to create almost any building you can possibly imagine. So, this chart lays out the 4 fundamental systems for us: form active, vector active, surface active, and section active. Now, what really unites all of them is how they solve the exact same problem, getting the building's load, its weight, safely all the way down to the ground. Let's break them down. First up, we've got form active. These structures are all about their shape. They're actually flexible, and they use their specific curve or line to channel forces perfectly. You see, they aren't strong because they're rigid, they're strong because they're incredibly smart. Just think of a suspension bridge, right? Its massive cables are in what's called pure tension. They're just pulling. Or picture a classic stone arch, where every single stone is in pure compression. They're all just pushing against each other. It is just elegance in action. Next up, we have vector active systems. And the dead giveaway here is the triangle. It is the strongest shape, and for a really good reason. It takes all these complex, multi-directional forces and breaks them down into simple, manageable lines of either pushing or pulling. This is what you see in the trusses holding up a railroad bridge, or in that incredible, complex web of a geodesic dome. Think Epcot. The key is there's no bending happening here. It's just pure, super efficient force transfer. Third, we have surface active systems. To get this, imagine a drum skin pulled super tight. Its strength doesn't come from any single point, right? It comes from the tension across its entire surface. And that's the whole idea here, strength through a continuous, unbroken plane. So think of concrete domes, or those cool folded plate roofs. The force spreads out across the entire surface. There's a name for this. It's called membrane stress. And this is how something can be incredibly thin, yet unbelievably strong. And finally, our 4th family, section active. Now, this is by far the most common system you'll see, and it's all about brute strength. It resists forces simply by being big and bulky enough to handle them. This is the classic post and lintel system you see literally everywhere. The beams and columns in your house, in your office building. It's really the workhorse of the architectural world. And not because it's the most efficient, but because it's simple, it's relatively cheap, and it uses really common materials like wood, steel, and concrete. Okay, so now that we have the 4 families down, let's zoom in on one of the most elegant of all, the surface active shell. I mean, this is where engineering and art truly become one and the same. Just think about an egg. I know, it's easy to crack with a sharp tap, but have you ever tried crushing one in the palm of your hand? It's surprisingly incredibly strong, and that's because its curved shape distributes the pressure perfectly across its entire surface. Architectural shells? They use the exact same principle. Now, these shells come in 2 main flavors. You've got synclastic, where the surface curves the same way in all directions, like a dome. And then you have anticlastic, where it curves one way along one axis and the opposite way along the other. Kind of like a horse's saddle or, even a Pringle. To find the most perfect shape for a structure, we don't need some kind of supercomputer. We just need a simple chain. When you hang it between 2 points, it naturally forms this beautiful curve called a catenary. And in this shape, every single link is in a state of pure tension. No other weird forces are at play. It's perfect. Okay, so you've got this perfect shape for handling tension, but what happens if you could just freeze that exact curve in place and then flip it 180 degrees? You get the perfect arch, A structure that was in pure tension is now magically in pure compression. This simple, brilliant insight is the secret behind the seemingly impossible buildings of architects like Antony Gaudí. It's just nature's perfection, simply inverted. It's amazing. All right, let's take these principles now and apply them to the ultimate challenge, building up, really, really up. Here's something that might actually surprise you. When you're building a super tall skyscraper, your biggest structural challenge isn't holding it up against gravity. Nope, it's stopping it from being pushed over by the wind. The race to the sky has really been a story of constant innovation. So first, we had rigid frames, but they kind of hit a ceiling at around 30 stories. To go higher, engineers added shear walls, these solid concrete cores. But the real game changer was a complete shift in thinking. What if the entire building acted like a single hollow tube? This one idea, from the brilliant engineer Fazlur Khan, just unlocked a whole new era of supertalls. As you can see on the left, you've got the frame tube of the original World Trade Center. In the middle, the iconic X-bracing of the braced tube, which you see on Chicago's John Hancock Center. And on the right, the bundled tube of the Willis Tower, where multiple tubes are basically lashed together for just incredible stability. So, we've covered a lot of ground, from the 4 structural families to the secrets of skyscrapers. But look, this isn't just about memorizing a collection of facts. This is really about getting a new way of seeing the world around you. The crucial point is that you now have a structural toolkit. The next time you walk through a city, you'll actually be able to decode the buildings you see. You'll see the hidden forces at play, and you'll understand the brilliant and sometimes simple choices the designers made to keep these amazing structures standing tall. So next time you're out, just walking through your city, look up. Is that building a simple section-active frame? Do you see the vector-active triangles in that bridge over there? Or the elegant surface-active curve of a stadium roof? The invisible language of our world is all around you, and now you know how to read it.